let's discuss perturbation theory in quantum mechanics. Specifically, time-independent, non-degenerate perturbation theory. Right. So, in quantum mechanics, perturbation theory is an approximation method or a scheme for describing complicated quantum mechanical systems. This is done with the help of their equivalent simpler quantum mechanical systems. And the idea here is to start with a very simple system whose mathematical solution is known, and then just add a very weak disturbance to our system, that is by perturbing or adding an additional term to the original Hamiltonian. Now, if the disturbances are small, then the physical quantities that are associated to our perturbed system can be expressed as some corrections to our simpler system. And these corrections, being small, obviously, then can be calculated using an asymptotic series. We'll call that our perturbation series. Alright, so as we said that we can write now our Hamiltonian as the sum of my original Hamiltonian of the system, that is the unperturbed Hamiltonian, plus some perturbed Hamiltonian. I'll say that it's H1, right? So my unperturbed Hamiltonian is H0 in superscript, and my perturbed Hamiltonian is H1. Alright, now we can say that let's expand my energy eigenvalues and my eigenstates in a perturbation series. So this is my eigenstate and this is my energy eigenvalue. Right. Now what I can do is I can expand these, so I can expand my eigenstates as n0. This simply means this state is now the zeroth order correction, or it is the original eigenstate of our simpler problem. And we can add very small disturbances, so with those our eigenstates can be written as n1. We can add a lot of them, so we'll have n1, n2 and so on. Alright, now we can do the same thing for En. We can expand it in a perturbation series, and so we'll get En0, that is again our energy eigenvalue for our simpler problem, that is unperturbed, and then we can add some perturbed terms to it in such a way. So E2n and so on. Right. Now we can say that these go up to some kth order, right? And as the kth order increases, the terms gets smaller and smaller. Alright, so we have that out of the way. Now let's again recall that when my Hamiltonian acts on my states n, they return me with a constant energy eigenvalue and the state n, right? So I have written this equation a lot of times, in fact I think in all of my previous videos, so it's pretty obvious. It's the eigenvalue problem, right? Okay, so now we have defined our Hamiltonian in such a manner, right? So all I'm going to do now is substitute this Hamiltonian in this eigenvalue equation, and I'm also going to substitute the perturbation series expansion for my states n and my energy eigenvalues En. So let's go ahead and do that. So when I do that, in my H I get H0 plus H1. I'm sorry if there was noise before. I had my fan on, so I just turned it off. And then Okay, let's get back here. So this is my Hamiltonian, and it acts on my perturbation expansion of my n's. So n0 plus n1 and up to so on, right? And it gives me en1 plus it gives me en0 okay, en0, then en1, en2, and up to so on, right? And then it obviously returns me with my eigenstates that are again n0, n1, n2, or let's just say up to so on, right? You get the idea. So now, if that's the case, let's first look at our zero order terms. That are the terms where you have h0, n0, e0, right? So that just returns you back to your simpler problem eigenvalue equation, and we know how to solve that, right? And it is obviously then independent of h1, that is the perturbed Hamiltonian. So let's go ahead now and look at the first order term. So from my above equation, if I look at the first order term, let's look at this equation over here. This equation comes from the previous equation that I just wrote. h0 n1 plus h1 acts on n0 is equal to en0 en0 n1 plus en1, that is first order, and state in zero order. Alright, so let's name this equation. I'm going to call this equation star. Equation star, right? Okay, now let's do something to this equation. Let's dot it on both sides of the equality with my bra in n0, this bra, okay? So when I do that, when I operate this above equation star with this n0 on both sides, so let's see what will happen. When I operate it to the first term over here, first what will happen, h0 will act on n1, right? And n0 will also operate over there, but the n's are orthogonal. n0 and n1 are orthogonal to each other, so they're going to cancel out and we're going to get 0. So first term is going to be 0, and then my second term will be my first term is also going to be 0, because it's obvious that we can see that my Hamiltonian is unperturbed and it's acting on my perturbed eigenstate, right? So the second term, let's look at the second term. When I operate this n0 on my second term over here, it will give me n0, my h1, and my n0. This term in fact is very important, right? Okay, now let's look at the right hand side of the equality symbol. Again, I'll get my first term, this one, as 0, with the same reason that en0 is my constant energy eigenvalue, so I can take that outside. And when I operate with this bra on this ket, so because n0 and n1 are orthogonal to each other, this will become 0. And on my right hand side, my en1 is constant. I can take that outside, and then I can take the inner product of n0 and n0. But then remember that my states are normalized, and if my states are normalized, this inner product n0 will go to 1, right? It will be 1 because my states are normalized. So if my states are normalized, that goes to 1. What am I left with is that my en1, this en to the first order then is equal to n0 h1 n0. Now this over here, this equation is my first order correction to my energy eigenvalue, right? So what is this? This is basically the expectation value of my perturbed Hamiltonian in my unperturbed states, the states that were of the simpler system, right? So this is how I can compute my first order correction to my energy eigenvalue, right, to En. So now that we have computed the first order correction, let's go back to our equation star that you can see above, and let's dot it with this thing right over here, M0 unperturbed M states, right? And it is very important to note that M is not equal to N. That is why we are basically choosing some other letter M, that these two states are not equal, right? Okay, so when I do that, when I dot my equation star above with this M, what I get is, let's do it over here, M0 H0 N1 plus M0 H1 N0. All of this is equal to my M0 En0 N1 plus my M0 En1 N0. Now, the reason that I'm doing this is that what I want to find now is my correction to the eigenstates of my system, right? So what I'll get now is the first order correction to the eigenstates of my system, right? So with the above equation that I just wrote over here, I'll go back here, the equation that I last wrote down here, I'm going to use this and I'm going to write this equation in another representation over here, which is just, I'm going to move some terms around and I'll write it as M0 N1 inner product is equal to my M0, the matrix element of my perturbed Hamiltonian, that's what this is, over E N0 minus E N1, right? Okay, so with this in mind, all I've done over here is rearranged this last equation over here and wrote it down in this form, right? Alright, now let's recall some things from our linear algebra in Dirac notation. Note that my n inner product, which is equal to 1 for my normalized eigenstates or wave functions, can also be written as in such a way: n0 plus n1, that is perpendicular component, plus n1 parallel component of n1 over here, and times its dual vector n0 plus n1 perpendicular component plus n1 parallel component of n1, right? And let's close our brackets over here. Now this equation over here can also be written as the inner product of my n zeros plus n1 parallel component inner product with n0 plus my n0 inner product n1 parallel component, right? And we can have higher order terms as well, which I'm just going to write it like this, equal to 1. Alright, now this can further be written as my n1 parallel component n0 inner product plus n0 inner product with n1 parallel component plus some higher order terms again. So this is not a theta, it's representing the higher order terms, right? And all of this equal to 0, right? So we are going to use this now, because this equation over here is going to tells us or implies that this inner product that I have over here, n0 with n parallel 1, the parallel component 1, is equal to some iota times alpha, right? Where my alpha is real, right? Now we'll use one of the quantities, that is that my exponential iota alpha is equal to 1 plus iota alpha. Now this is just the series expansion of my exponential function with the power iota alpha, and here I'm again neglecting the higher order terms, right? So with this I can then write my n states as following: n0 times exponential iota alpha plus my sum over my states, all such states where my m is not equal to n. So I don't want my same states over here, and m0, this is the outer product, and here I have my perturbed Hamiltonian and n0. All of this over e n0 minus e m0, right? Now we are getting somewhere from here. Now the only problem that I have here is with my exponential iota alpha, this term over here, right? But there is a very neat way to get rid of it, because of the fact that my n states has some arbitrariness in its overall phase even after it is normalized. So let's change its phase by a factor of exponential to the power negative iota alpha, and what this does is then it gets rid of my phase factor that is multiplying with my zeroth order eigenstate, and it will do absolutely nothing to the first order piece up to this order. Which order we are talking about? We are talking about the first order correction to my eigenstates, right? So I'm going to multiply with exponential negative iota alpha this term over here, right? So obviously when I do that, this cancels with this because they're opposite signs, and with that, calling the perturbed eigenket with the new phase also n state or nket, we get the result to the first order, and that result to the first order can be then written as n state is equal to some unperturbed state, not some, but actually the unperturbed state, that is the state of our original or a simpler system, plus this term over here. So what is that? That is m not equal to n sum my m0 outer product with m0 h prime or h1, that is my perturbed Hamiltonian, n0, all of this over e n0 minus e m0. So this equation over here gives me my gets to the first order, right? So my energy, I'm sorry, not my energy, but my eigenstates or my wave functions corrected up to first order. So if I just want what is the first order correction, that is this term over here, and it is extremely clear. Why is it like this? Because it is, my n was a series expansion, if you remember, and this term over here is my unperturbed eigenket, and then all of this term over here, the next term, is then my perturbed eigenstate, right? And perturbed eigenstate up to first order. So let me write it down here that my eigenstate corrected up to first order is equal to sum over all the states that are m is not equal to n, that are not same, m0 outer product, my perturbed Hamiltonian, and n0, right? All of this over my zeroth order energy eigenvalues. The difference. All right. So now we have determined the eigen states corrected up to first order, right? Now let's go a bit further and also determine what would be my energy eigenvalue corrected to second order, right? So to do that, well, what I'm going to do now is I'm going to determine this thing over here, right? What is this quantity? So again, to do this, let's recall my equation that was that my h0 acts on my n corrected up to second order. This equation that I'm writing over here comes from the first equation that I wrote, where I opened my Hamiltonian in its original Hamiltonian and the perturbed Hamiltonian, and I also expanded my eigenstates and eigenenergy values, right? So from there, I'm recalling this equation. Let me write it down. Is equal to E0n n2, that is my state corrected up to second order, not n squared, and E1 N1 plus E2 N and my N0, right? So again, I'm mentioning that this equation comes from the equation that I opened previously by opening my Hamiltonian in terms of perturbed and unperturbed and expanding my eigenstates and my energy eigenvalues, right? Okay, so let's call this equation over here equation double star, right? So now if I dot this equation double star with my N0 in bra, then what happens, right? We can immediately see that when I do that, my first term in this will vanish and this over here will vanish as well, and also this term over here will vanish because of the fact that my N0 and all of my N states are orthogonal to each other, right? So N0 with N2 will go to 0, N0 with N1 will go to 0, and my first term over here will also, this term will go to 0. Alright, so let's do it. Let's dot my N0 with the equation star star. What do I get? I get N0 H0 N2, this matrix element, plus N0 H1 and my N1 is equal to E0 N N0 N2. Again, I'm doing this because my E is a constant energy eigenvalue, so I can take it outside. And well, let's continue. I'll have plus E1N N0 N1 plus E2N N0 N0. Now, the normalization condition implies that this over here will be 1, this will go to 0, right? So they will go to 0, and also this thing over here goes to 0. So with that simplification, I'm left with, on my right hand side, En2 times 1, and on my left hand side N0 H1 N1. Now what does this tell me? This tells me that my energy eigenvalue corrected, or the correction to second order, is equal to this thing over here, which is nothing but the expectation value of my H1 in N0 and N1, right? Or it's the matrix element of my perturbed Hamiltonian. Now, if I recall that I have already found out my N1s, so I can put that value in here, the value of my N1 that I previously found, and when I do that, I'll get my E sub N super 2 is equal to sum over all the states where M is not equal to N, N0 H1 M0, right? And again M0 H1 N0, right? All of this over E N0 minus E m0, right? So all I have done is I have substituted the value of n1 from my previous expression that I had derived for n1, that was over here, this expression over here. I have simply substituted this expression over here into this n1, right? So when I do that, this over here is what I get, right? And this over here can then further be written as my E second order is then equal to n the square of, let me first write it down, h m0 modulus square over E n0 minus E m0. I have missed out the summation sign that I must have, so let me just write it down over here, because all of these states, they're going to be summed over. So I'm going to write this summation m is not equal to n, and what does this gives me? My second order energy eigenvalue. Alright, so the term over this fraction is simply from the fact that if you look over here, I have this thing, and this thing is nothing but the mod square of this term over here, right? So this equation over here gives me my energy corrected to second order, my energy eigenvalue of my system, right? So what I have done is I have taken my original system, I have perturbed the system, and then I have expanded my energy eigenvalues and my eigenstate vectors. In a series expansion, I have, with the perturbation of my system, the Hamiltonian of my system had also been perturbed, and then I substituted for that perturbed Hamiltonian the unperturbed plus the perturbed part, and I acted on my states, which was again this equation, the eigenvalue equation over here, and I solved it. So solving that, I got my solutions to my energy, corrected solutions to my energy values and my eigenstates. So with that, I'll conclude this lecture and this video. And if you could not imagine the beauty of this perturbation theory at the start when I started this video, now you can see that how beautiful this theory is, that you can simply take a very simple system and solve a much complicated system with perturbation theory over here. This over here was time independent non-degenerate perturbation theory. If you would like me to do the time dependent non-degenerate perturbation theory, mention in the discussion box below, and we will continue from here next onwards. Thank you.